Matrices. Determinant of a 2 by 2 square matrix. The determinant of a square matrix is used to solve problems. Using determinant to find area of a parallelogram, which is 2 by 2 matrix, or triangles, or volume of a parallelepiped, which is 3 by 3 matrix. Using determinant to explain transformation matrix. Using determinant to solve simultaneous equations to find consistencies or non-consistency. Consistency means finding solutions, and non-consistencies mean no solution. For 2 by 2 matrix determinant, if we have a matrix A and we have A, B, C, D as the elements, we can find determinant. This is a symbol for determinant of A, or can be written as determinant A, which is now that you put the elements of A in the determinant by saying A times B minus B times C. That's the determinant of A 2 by 2 square matrix. Now let's explain where this is coming from. If you consider a linear system, what we mean by linear is that if you have x to the power 1 or y to the power 1 or z to the power 1, that's what we call linear system, because the exponent or the power is 1 and you can mix them. So x plus y is still a linear system. We're just adding the linear system. So that's x to the power 1, y to the power 1. So the linear system exponent equals to 1. Exponent is the power. Here are two linear systems, ax plus by and cx plus dy. And now we can turn that into matrix by writing A equals to A, B, C, D in the matrix form using the coefficient. So the coefficient now has been placed in the matrix. So this is the same matrix with the elements A, B, C, D. And so these are the x coordinate and y coordinate. If we turn that into a graphical form, and you got a vector AB and CD. So those are the coordinates here. And what I'm going to do is to turn that into a parallelogram. So that will be parallel to that, and this will be parallel to that. So what I can do now is put those arrows in there for the parallelogram. And now I've got new coordinate. So that point will be A plus C, comma, and B plus D. So what I need to do now is to find the area of the parallelogram. So in order to find the area of the parallelogram, I'm going to use the graph. So I'm going to turn that into a triangle, and I'm going to draw that line down into another form of triangle. I'm going to close that line there, and I'm going to draw that line across and close that. Okay, it's not the best parallelogram, but so we have the distance here, and that distance is A. We got that distance here, we got that distance here as well, and we, in fact, if we could close this bit here as well. So we have that distance here as well, and that distance from there to there is a distance there, and that's a distance there. We've got a distance here as well, from there to there. So we've got distance there, and another distance there. And we have a distance here as well, and a distance there. So what we want to do, close that distance here and there. That's a distance there, and that to there. That's a distance there, and that distance from there to there. So that distance is A, so that is C, and this distance is D, and that distance is B. So that distance here is B, and that distance here is D. Okay, I can split this up as well into two distances, so that's C, and from there to there is A. So I've got a rectangle, and inside that rectangle I've got composite compounds, two triangles which are the same. So that triangle here will be the same as that triangle over there, and this triangle here will be the same as that triangle over there. This will be the same as that over there. What I then need to do is find the area of the rectangle on the outside and take away the area of the composite compound. And so the area of the rectangle on the outside will be A plus C times B plus D. So let me take that and put it over here, and I need to take it away, the area of the triangles. So the area of this one here which is two of them. So that's C, BC, B times C, and that one too is B times C. So those two areas are the same. My drawing is not perfect, but they're the same. So I can take that away, minus BC and BC again. Also, I need to take away the area of this triangle here and that triangle because they're the same. And I need to take away area of that triangle too. They're the same as well. So we'll do minus two of them are half, well, AB. So that's AB. And then minus 2 are half, well, so that will be CD because these are CD, C times D, and that's C times D. So we take that away, CD. And that's what we need to simplify. And that will be the area of the parallelogram. Which parallelogram? This parallelogram here. So that will be the area of that parallelogram. And to finalize that, we cross multiply, we expand this one here. A times B will be AB, and we go to A times D plus AD, and we have C times B, that would be BC, and C times D, that would be CD plus CD. And then I need to take away minus BC minus BC minus this one is 2 over 2, that's 1, so that's minus AB, and minus 2 over 2, so that's CD. Some stuff cancelling out. Well, there's AD here minus AD plus AD, that's gone. CD here plus CD minus CD, that's gone. BC plus BC minus BC, that's gone. AD minus BC. That's exactly what we got from the determinant. So the determinant of that matrix A, which is the determinant of A, and that can be written as ACBD as the determinant sign, is equal to AD minus BC. AD minus BC. That's what we write. AD minus BC. So that's a proof that determinant is used to find the area of a parallelogram of a 2 by 2 matrix. And where is that useful? Well, so this is useful when you have a graphical situation like a vector. So if I have a vector, an area or a matrix A, C, and B, C. Let's make that matrix say 4, 1 and 1, 2. And we can graphically demonstrate that. If I have a unit, so if I split that into 4, and that's 1, 2, 3, 4, and this is 1, 2, 3, 4. Now, what I can do is so this one is called a unit vector. That unit vector is x is 1, y is 0. So I can write 1, 0 for that vector. And this vector here is a unit vector. X is 0, y is 1. So I can write that as 0, 1 as a unit vector. And I can then transform that unit vector into that vector. So I can call this one 4, 1. So I can call this vector 4, 1. I'm transforming this one here. Let's call that the x there. I'm transforming that into this vector 4, 1. Or 4, 1 there. I want to get a new vector, which is I'm going 4 along, 1 up. So now my vector there. So that'll be my vector 4 along, 1 up. So that's vector 1. And 1, 2, x is 1, this is 2, so that's 2 along. So that's my vector number 2. And that's V2. So I'm calling this one, the V1 is 4, 1. I just use that as a vector now, 4, 1. And the V2 is 1, 2. You still get the same thing, you do it that way. I can then turn that into parallelogram, right? That's better. And this would go that way. Okay, so that is 5. So that'll be 5 along and 3. Okay, but what this is trying to explain is that the area of this unit vector, when you transform it into that matrix vector, that area is also scaled up to the area of the new parallelogram. So if you have say a strange object in the little square matrix like that, and you want to find the area of that object, and you scale it up to that bigger matrix, and you want to find the area of the bigger matrix. Say you know the area of the small object. Say that was 0.5 units squared. That's the area of the small object in the little matrix here. And we can work out the area of the big object in the scale up matrix by applying determinant. So the determinant of the determinant of A will be 4, 1, 1, 2, and that will be 4 times 2, which is 8, minus 1 times 1, which is 1, and that equals to 7. So now the area of the big object will be 0.5, and you times that by 7. So 0.5 times 7 will be 3.5 units squared. And so that's the application of the transformation matrix.